All right, so today I'm going to be explaining this important paper, which is not related to diffusion, it's related to normalizing flow, and I should say why it is related to in this playlist. So, normalizing flow, the continuous version of normalizing flow, you can write flow as an integral of solution in terms of this velocity in dt. So, it's a solution. So this solution can be a map as well. That's why this flow matching technique is much better than continuous version of normalizing flow. And so if this is flow matching and if it is diffusion, so here it is the intersection, which is a stochastic interpolant. For example, we can say a Schrödinger bridge. We can define a Schrödinger bridge. Or anything inside is very interesting. So let's carry on this AAAI in this year, 2025, from this great company in Silicon Medicine. So we propose a hierarchical normalizing flow model for generating molecule graphs. The model produces new molecular structures from a single node graph by just recursively splitting that node in every two nodes. So splitting every node into two. So one node becomes two nodes. So, but all operations are invertible and can be used as a plug-and-play module. The hierarchical nature of latent codes allows for precise changes in the resulting graph. Perturbations in the top layer cause global structural changes, while perturbations in the consequent layers change the resulting molecule marginally. The proposed model outperforms existing generative graph models on the distribution learning task. So we show successful experiments in global and constraint optimization of chemical properties using latent codes of the model. So this paper is very important for drug discovery. And so when we have a discrete version of normalizing flow, we have a sequence of normalizing flow, because the problem is this determinant of Jacobian, it's computationally expensive. And what is MolGrow? So it produces new molecule graphs from single node by just, as I said, recursively dividing every node into two. So finally, the graph has 2 to the L, because L is the number of node splitting layers in the model. To generate graphs with fewer nodes, we add special padding atoms. We choose n to be large enough to fit any graph from training dataset. Full architecture combines multiple levels to generate latent codes from a graph. Each level separates nodes, merges node pairs, applies multiple blocks and linear transformations. So we have these L codes. And each level separates nodes and merges node pairs. So on the right, you see that each block applies 3 channel-wise transformation and 2 real NVP layers. So this figure 1 shows the architecture of MolGrow, which has L invertible levels. Each level has its own latent code with a Gaussian prior. On a forward path, each level extracts the latent code and halves the graph size by merging node pairs. On the inverse path, each level does the opposite. It splits each node into 2 and adds additional noise. To avoid fitting discrete graphs into a continuous density model, we dequantize the data using a uniform noise. So this node merging and splitting example you can see here, that for a 4-node graph, you can see that we concatenate features of nodes V1 and V2 and edges to get new node features. So we also concatenate the edge features. So splitting operations slices merged graph nodes and edge features. So in this direction, we have a split. Each node becomes 2. Each node becomes 2. And the other direction is merging. For merging, we concatenate. Concatenate E1C, E14, E2UC, we concatenate them. So we use node merging and splitting to control the graph size. So it produces a latent vector for each level. We derive the latent codes by separating half of the node and edge features before node merging and impose Gaussian prior on the latent codes. During generation, we sample the latent code from prior and concatenate it with node and edge features. Remember, this paper is in 2025, so it's not an old paper. Here, the basic building block has 5 layers. The first 3 layers, the permutation, linear, active norm, is just one by one convolutions. And each layer contains 2 transformations. One transforms every node and other transforms every edge. And here, similar to other graph attentive graph convolutions, they use multi-head. Also, positional encoding, you can use sinusoidal positional encoding. So the input is the complete graph, the node feature matrix, and the output is the transformed complete graph of the same dimension as VNE. So here they use GRE, then here again for edges they use GRE, for nodes they use GRU, gated recurring unit. And here they compute the messages when you transfer using a fully connected neural network, F theta. And here they have balanced padding. So the input is list of fragments where each Fi, F1, for example, these fragments contains atom indices in the i's fragment. Fragment level of graph generation is another generalization, because you see it's 90%, 95% of the papers you see on graph generation using diffusion, they just add noise to the nodes and edges and adjacency. They don't go at the level of the fragment. For example, this set of nodes can be a fragment. For example, it can have this structure or different structures. It can have different structures, and these are things that are repeated. They are motifs of the system. So instead of just flipping one atom, you can even replace one atom with one fragment, because these fragments, when a fragment attaches to the sites of a protein, this is what happens actually in biology, in practice, in our body. So why not we use it, we draw inspiration from that and use it. Why don't we see it in ICLR and NeurIPS papers? It's because most people follow others. And also it needs a team, it needs a discipline to work on these things much more carefully. If you look at the elbow, when they write the elbow, everything is the same. But instead of node level, you can have a combination of node and fragment. Instead of edges, you can have higher levels. So these are the things that we usually don't see in any ICLR, ICML, NORIX paper. And this is the distribution learning metrics on Moses dataset. For example, they compare graph variation autoencoder with MolFlow. The Moses dataset is important. Also QM9 dataset and Zinc dataset, they are also important for graph generation. For validation, we know validation, uniqueness, FCD, novelty. These are the things that we see in all graph generation papers when they want to compare. But nowadays people scaffold and people are inventing new measures to see, because the current measures are not enough, especially when you want to distributions of the true distribution and the generated distribution. Distributionally we need new measures. So this is for QM9, samples from MolGrow in QM9 dataset. This is Zinc 250K dataset. And this is Moses, trained on Moses dataset. Spherical interpolation between two molecules in the latent space of MolGrow. This is resampling of latent codes on different hierarchical levels, trained on Moses dataset. And this is the best molecules in intermediate populations for penalized actinol water partition coefficient.